Good evening, everyone. My name is Sam Nasser, and this is the Cleveland C# VB.NET user group. A little bit about the group. We meet every month. Meetings are free of charge and open to the public, and we cover a variety of topics related to .NET. You can find the meeting information posted on meetup.com at the link listed at the bottom of the slide. I'd like to give a big thank you to our sponsors, PostSharp and DevExpress, for sponsoring the raffle prizes, which will be handed out using the eval form. I'd also like to thank the .NET Foundations for sponsoring the web hosting. And last but not least, NIS Technologies for the virtual meeting space. Also, I'd like to give a big thank you to Manning.com. They're offering us a 35% off discount on a selection of books. And you can find those books over at dealings.manning.com. And the link will be made available later in chat. It utilizes the discount code MTPCLEC21. Some general information, please keep in mind participation is always encouraged. And like I always say, the only stupid question is the one not being asked. So feel free to jump in with any questions you may have. However, when not speaking, kindly ask you to mute your microphone to prevent any background noise. Also, we like to keep it casual but organized, meaning we like to give the opportunity to jump in with questions or comments, but at the same time, provide enough time for our speaker to go through the slides and the demos. Lastly, the presentation will be recorded and will be posted on YouTube with the link provided later. So for tonight's feature presentation, Seth Juarez with the topic, Ask Me Anything on Machine Learning. Seth is a principal program manager for the AI platform at Microsoft. He has a master's of computer science from the University of Utah, and he's also the host of the AI Show Live. You can follow him on Twitter at Seth Juarez. And so with that, let me turn it over to Seth.
All right, so this is more of a ask me anything. I'm going to start with obviously the most important question, which is what is machine learning? And then I'll just get into stuff, but I would rather answer any questions you might have. And if I'm too loud or not loud enough, let me know. I can make some adjustments here. I don't have any slides, but I do have some stuff to show you if that works okay with you all. So before I get started, I'd love to just start with, what are your questions? Do you have any questions about machine learning? The first one that I'm going to answer for sure is, what is it? And then the other that I'm going to do is, how is it done? Oh, that looks like dome. That's embarrassing. Oh my goodness. How is it done? How is it done? Any other questions that I should add to this list? And there's only 7 of us here, so we can answer every one of your questions today because
what are the applications of this machine learning in the business area?
Okay. What are the applications? Love it. I'm going to put a little red star by this one since it's a community asked one. Okay. Any other ones?
I have one.
Sure.
When using ML.NET, when you're training it on a specific set of data, it goes through approximately a dozen different algorithms. And if you give it more time, it'll still continually repeat those algorithms again, but then you'll get better results. So why is it that if you're using the same algorithm repeatedly over time, you're getting better results versus just the first time you're running it?
I love it. Okay, cool. I can answer that one too. Any others before we move along into the stuff?
Yeah, I had a question. I was just wondering, is there any good place to do a getting started, kind of like a hello world kind of thing for machine learning? I know there's tons of info out there, but I didn't know if there was a best place to dive in.
Yes, I will make sure to get to that one. And then one more. One more. It's my cricket sound effect. It means that my volume is too low. There we go. Okay. All right, we'll start with those. If there's any that come up after, feel free to hit me up. So I'm going to start with what is it? So we're in the what is it this stuff phase, and then I'll get into how to do it. Now I know this is a .NET user group, and so apologies, but state-of-the-art machine learning is generally done in Python. Sometimes R. Probably not in C#, although C# can be used to consume machine learning. ML.NET consumes models, but generally models aren't trained in ML.NET in the industry. Now, I'm not saying that y'all don't. I'm just saying in general, the industry. So the question that we're going to start with is, what is it? Okay, and this is a fun question, because generally when we have a problem in machine learning, when we have a problem with computer, we want to solve a problem with computers, what we do is we first figure out what the problem is, and then we come up with a series of steps to solve, and then gosh, I'm so terrible at writing. We come up with a series of steps to solve, and then we codify this into some kind of program. And then we ship this program out in a box, and then we get the problem, and then the program's like, doot, 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 and then out comes the right answer. So this is how we program. Now this is obviously super simple and really dumb, and this might be like a function, for example, that we want. So for example, I need to know, if this is in miles, I need a function that converts it to kilometers, right? That's the problem. So what are the steps to solve it? Well, it turns out that there's 1.6 kilometers per mile, and so you might have a function that takes miles and just multiplies it by 1.6, and then that's our program, we ship it. Obviously, this is the dumbest thing I've ever talked about when it comes to programming, but if you think about it on a larger perspective, it's basically programming is just bigger than that. The problems are bigger, but ultimately we end up writing a series of functions. Okay, now, as I'm talking, if anything doesn't make any sense or you don't agree with what's going on, since there's not a ton of us here, you can just interrupt me. I think that would be much better. Just be like, wait, what are you saying? So this is generally this is what I think of as programming. So this is what a programmer does. Now, what machine learning does is it flips this entire idea on its head. And the reason why it does this is because the problem isn't so obvious on how we would solve this with the series of steps. So what machine learning presupposes is that, let's just say, for some reason, converting between miles and kilometers is just completely mysterious for some reason. What machine learning does instead is we, again, start with a problem, but instead of creating a series of steps to solve it, we give the computer some data, and it produces the program. Okay, and this is where it's like, what? So I want to stop and pause there, because this is really the key concept that I think once we understand, everything else kind of makes sense. So the problem is we need to convert from miles to kilometers. Instead of coming up with a series of steps to solve it, in our case, we just multiply by 1.6. So the number comes in n, and then this is the program. We write it up. The idea is that we give it some data, and the computer figures out the program, or in this case, the function. These programs are called models, machine learning models. So I'm going to stop there, and I want you to ask me whatever question came into your head, because this seems weird, but I want to make sure that I can answer your question. So questions about this one little thing.
So I can see how this would work with linear data.
Yes.
But maybe I'm jumping too far ahead. But what about things like object recognition, And then we get into the world of Lewis, which I'm very fond of.
Sentiment analysis, entity recognition, that kind of stuff, right? What does this have to do with anything, right? I
I
see.
can
Yeah.
see, I mean, like I said, I can see it work with linear data, but then when you get into those other realms, that's where it gets very fuzzy for me.
Yes. It turns out that, and that is exactly the best question. The question that always surfaces, well, Seth, what does this look like for more complex problems? And then how do we build them? Right? Because it turns out that the machine doesn't just guess what functions it needs to write. You have to give it what I like to call a function. I did not mean to do that. So let me go back to this. We have to give it this function shape. As you astutely observed, Sam, basically, if you give the computer a bunch of things like here's the miles and here's the kilometers, right? If you give it 1 and then this is 1.6 and then you give it 2 and this is 3.2, right? You can do something like linear algebra and fit a line, and that line will eventually give you y, which is the kilometers, we'll say k, equals 1.6 times the miles plus 0, right? Which is this simple, easy conversion. This is called linear regression. It's easy. But what about other problems? Like, for example, the problem we're going to look at today is this one. How do I get the computer to look at this picture of me and tell me that I'm not doing anything, this picture of me and tell me that I'm doing paper, and this picture of me that I'm doing rock, and this picture of me that I'm doing scissors? Because that seems a little bit more complicated, right? And this is where we have to start getting a little bit more expressive. So I'm going to take a tiny digression from this, because I've just described the world of machine learning, but sometimes there is this concept of like, well, I've heard of deep learning. I've also heard of AI. How are those things related? So we just talked about machine learning, but machine learning is part of a larger universe of something called artificial intelligence, right? So machine learning is just a subset of AI. For example, if you've ever used Waze, it's using AI, but not necessarily machine learning. Or, like, if you want to build a tic-tac-toe game, this is really easy to do. To play against a tic-tac, like if you want to write a program that plays tic-tac-toe against you, you will use AI, but you will not use machine learning. Because in this case, there is a finite state of things that you can do and program. I'll give you an example. If I'm here and I put like, oh, here, there's 1, 2, 3, 4, 5, 6, 7, 8 places where you can put it. So from this starting state, you have, 8 options of things that you want to do. And you can enumerate them, right? So I'm going to put my X here. I can put my X here. So notice this starts making a tree. And then what you can do is say, if I put my X there, then here are all the moves that they can do with O. Do you see that? And so you basically build this entire space of the game in a finite way. And now basically AI is a glorified search problem. This is structured, more hard AI. And this AI we've been using forever. This algorithm, by the way, if you want to look it up, it's called Minimax search, and it's for adversarial search in games where you assume everyone plays optimally. The other one for Waze, that's basically trying to find the best path through a graph with weighted graphs, is this algorithm is commonly known as a star search, where you have a heuristic to search over perhaps an infinite space, but the environment is quite clear. Like you have point A and point B, and you have a weight, and you're trying to find the closest one. Obviously, if you're a computer science expert, you could see this being like a traveling salesman's problem, but everyone knows is NP complete. But in this case, this is a really rudimentary approximation using what's called a heuristic function. So this is standard AI. But then we get into problems where it's like, what's in this picture? Or find the word that's angry in this sentence. All of a sudden, the search space is fairly ambiguous. And so this machine learning is you give it data and the answer, and it produces a model or an algorithm, right? But you have to tell it, here is the model shape that I want you to use. And this will become clear in a second. You have to give it a shape. And then you optimize whatever the shape is until it produces an algorithm. And then finally, in this space, you have this other area called deep learning. For example, one of the machine learning algorithms we just talked about was regression. There's all sorts of regression. There's also some things called decision trees. You might have heard of that. Or there's something called logistic regression. There's XGBoost. There's something called neural networks. There's all sorts of cool shapes that you can give the problem, and then it optimizes across this shape with your data to produce the best answer. Now, deep learning is special because it's actually neural networks that are deep. And what does that mean, deep? Well, the depth of the neural network, in order to make it deep learning, really depends upon the marketing team. Hold on, I have a. Really, that's the truth. We don't know. It's just a neural network that's actually really quite deep that, figures out the problem. So that is the separation between AI for me, machine learning, and then deep learning. Questions on this little bit? Okay.
I'm good.
Cool. So now let's dive into some of the questions. How is it done? Now let's get into the applications because this is a good question. So anywhere where it's ambiguous as to how you might solve the problem with an algorithm that you have to hand code, and you're not sure how to do it, but you have a lot of data that gives you an indication of what the answer might be, that's where you use machine learning. That's the smell. So for example, things that are fuzzy, like figuring out the text on a handwritten page, or figuring out whose face that is, or another one might be converting someone's speech into actual text. Notice that it's hard to come up with an algorithm empirically that will do it correctly every time for everyone, but we have a ton of data of people speaking and their transcript. Or we have a ton of data of Seth making rock, paper, scissors, well, not a ton, but enough, and having a label that says this is rock, this is paper. Or a ton of pictures that have boxes around each of the objects in there, right? Notice it's not empirically easy to come up with an algorithm to solve that problem, but it's easy to have a lot of data to give to a machine learning model to figure out the solution to that problem. So did I answer this question to the satisfaction of the asker? This one?
Yeah, that makes sense. And if you can quote some business applications, I know I understand the concept of the machine learning.
Sure.
From your experience.
Yeah, we're gonna do this one next. Okay. So how is this done? And then we'll get to the ML.NET question. I am not a huge fan of ML.NET for a number of reasons, which I won't get into here, maybe another meeting. But I will tell you that there are some cool stuff to do inference. And so let me explain two things. There is this notion of model training, which is when you give the data and the answer and the computer figures out what the model is. That's called training. And then there's this portion called inference, where you use the model to make predictions. So I'm going to use those terms more often. Training is when you build a model, and I'll show you an actual model, an output, and you'll see inside of it. And then inference is when you use the models to make prediction. Now, you can train models the best way to train models is usually in Python, but for inference, you can use models anywhere. And ML.NET is an absolutely wonderful way to do model inference. And so you can plug these files into your C# programs. Now, again, a model that's built is just like any other asset in a development pipeline. Just like you have a jar file if you're doing Java, or an assembly if it's .NET, or whatever. The output of these files is pretty standard, and when you look at them, you start to get a sense for what these things are. Okay, so let me close all these things, and we'll start from scratch. So we have the data, and I'm going to move this. I was using a Wacom tablet, if you were wondering. So the data, this is the data, and instead of having a label inside the picture, it's basically the folder tells me the kind of picture it is. So notice that this is me, like, in various and sundry steps of me not doing anything, right? This is me not doing anything. This is me doing paper, and then rock and scissors. So the label, which is the right answer, is in here, and this is the data. And the way that I like to think about this is that these are all the x's, and for each one of these x's, this is the y, right? So given a pair of x, y's, we give this to some machine learning thing, and what it does is it produces a function that, given x, it will produce the right y. I'm gonna do this one more time, because remember, each of the pictures is an x, and the label, let's just say none, is the y, right? And we have a whole set of those. So given a set of x's and y's, we give this to the computer, and what it does is it produces a function that, given an x, it will produce a y for you. In our case, we're giving it an image, and it's saying rock, paper, scissors, or none. Are we good on that one? So this function is what we call the model, right? And this is what we call the data. This particular problem is a supervised learning problem, because we're giving it the thing and the answer, which is the image and the answer. Questions? Good so far? Now, again, I go as fast or as slow as you want, because like I said, I remember learning this the first time. I was like blown away by it. Sam, looks like you had a question.
No, actually, I'm good with that explanation, but Vince had a question, though.
Yes.
Yeah. Hey, Seth. This is more about what we were talking about before, about how to apply machine learning.
Yes.
I've been involved in a couple of machine learning projects, and it always seems like they fail. They don't really go anywhere, and I just wonder if it's just a bad use case for it. One example, maybe it is more like the traveling salesman example you gave, of really logistics of you've got something that needs to be delivered, and there's several different warehouses that are available to start out at, and a bunch of data to see delivery times and deciding which one to use in which case. We could solve it with an algorithm, but it feels like there's a lot of data out there to look at, and machine learning might be able to guide us better. Is that a good use case, or is that something that really doesn't fit?
It could be. For example, one of the things that I've seen used with machine learning is, and I don't know if it's quite similar to what you're saying, but how much of a product to stock on a shelf, right? Because you don't want to have too much, but you don't want to have too little, because you miss an opportunity. In this case, I would have to look at the specifics. But to answer your sentiment in general, a lot of machine learning projects indeed do fail for a number of reasons. The first one might be that maybe you don't need machine learning, and you're trying to force a round peg in a square hole, or vice versa. I'll give you an example. Someone from Australia reached out to me, and they were like telling me about this machine learning project that they wanted to do, and I said, hey, my guy, I think this is awesome, but it feels like a database lookup, not machine learning, like a query with a fuzzy search. And he was like, no, it feels like machine. I'm like, no, I can even write out the query for you right now. And so sometimes it's the misapplication of machine learning. Second, let's just say a machine learning model was built correctly. We have found in our research that a large number of successfully built models hardly make it into production because of the transitioning the chasm between you have a model file, how do we put this into production within our DevOps pipeline? And that gets into this notion of MLOps, which is hard. If any of you have ever gone through a DevOps transformation at your org, you know that's hard. It takes the union of people, process, and product to enable the continuous delivery of value. And doing things in a DevOps way, even on its own, is hard. When you start to add, competing interests when it comes to data and models, and then people not knowing what these models do all the way, and then shipping it out, it becomes a little harder with all of those orthogonal concerns. So, yes, a lot of machine learning projects indeed do fail, either because of misapplication of the technology or using the wrong model, or a misunderstanding of how to use the model in production. Does that answer your question, Vince?
Yeah, I think so. I think it's a little bit of all those things. It seems like they get stuck in the modeling phase forever, where there's just this constant experimentation and nobody's really putting out any data for us to say, hey, this may be right, this may be wrong. Let's grade it together and make it better. I feel like it's just always stuck in this experimentation phase. And
Let me add another question here, because I think you're hitting on something that I did not. You're kind of like having the unasked question. How do we know if we're making progress? Right? Because it feels like a black box. Am I getting that right? And it's just like, what the heck's going on over there? Is that what you're saying?
yep,
Okay,
yep,
cool.
you machine learned my brain.
Yes, and I'll show you how you can actually do that. There's a way to do this.
Cool.
But again, this is all nascent. Like, I think for some of you all, it's the first time you've heard such a dumb explanation of machine learning where you're like, that's really it. This is the dumbest. Machine learning really is just a lazy way of writing functions with data. But marketing won't call it that. They'll say AI, and it's because, that's how you sell stuff. But I make stuff just like you all. Okay, so let's go back to this particular problem here. So there's the data, and there's the. I'm going to delete this so you can see that I'm making it from scratch. Okay, so I'm going to use notebooks and Python. Now, excuse me for using Python. I don't want you to think that this is a bait and switch. But Python is actually a really cool language. I did .NET Dev for nigh a decade, and then I went to grad school, and they used Python, and now Python is just being used everywhere for machine learning. Happy to talk about options in C#, but this is really where all the innovation happens. And so, although I have been trying to get some of our .NET friends, because I work at Microsoft, to consider certain things, and I'll let you know how that goes. So I'm just going to go through the steps of how you would do this in something like PyTorch. The first is we have to convert X, which is the images, into numbers that are consistent. What the heck does that mean? I'll show you. So a picture really is just like a 3D matrix of numbers. Now you might be saying, what do you mean? So in this square, there's red, and this square there's RG green, and this one there's blue, right? So that's what a picture is. It's a big box, a big cube of just numbers, right? And it's the height of the picture, right? This is the height, this is the number, this is the width. Now, in order to get this machine learning algorithm or model to do any prediction, we need to have them all be the same size. I mean, now I'm going to start to get into how these things are implemented, and you're going to be like, oh, this is how it would be. How else could it be? So you can't give it any arbitrary picture. You have to do some pre-processing to make sure they're all the same height, the same width, the same colors. Like, for example, one thing that I did not mention is you can have this little transparency layer called the alpha channel. That makes it so that it has it's a 4D tensor, or these things are called tensors, by the way. It's just like a matrix with numbers in them. That's all these things are. So the first thing we're going to do is we're going to figure out how to make all of these things be the same. So this is called a compositional transform using PyTorch, and I'm a fan of PyTorch. And there's a PyTorch, there's a torch.net that you can use, I think, that maps directly onto this, because all the back of all this stuff is like C++. So notice that what we're doing is this composes a bunch of transforms. This makes a function such that when a picture comes in, we resize it to 256. We center crop. What does this mean? This means that if the picture is like rectangular, we resize to 256, and then we center crop out the middle so that it's a perfect square, 224 by 224. Right? Then this converts it to a tensor. Now you're looking at this, you're like, what the freak does this mean? Well, all this means is that instead of having numbers between 0 and 255, I think this forces it to have numbers between like either -1 and 1 or 0 and 1. I don't remember which one it is. But basically, we're making numbers smaller, because in math, it turns out that if you have big numbers, those big numbers start to compound if you're doing multiplications and divisions and whatever, and you can overflow. So, any questions about this? So this transforms the x's. This thing transforms the y's, right? And all this does is, if it's a 0, like this is none. If it's 1, it's like rock. I don't remember what they are. We'll find out. I deleted it, so it's not there. What this does is this converts these numbers into positional vectors. So there's going to be 4 of them: rock, paper, scissors, and none. And so, this is like the crappiest. So if it's none, here I'm gonna make this really nice so everyone can see what I'm talking about. So 1, 2, okay, and then 1, 2. Okay. So this is the first one. If there's a 1 on this one, 0, 0, 0, this means none. If 0, 1, 0, 0, this means rock. And this will become obvious at the end why we do this. 0, 0, 1, 0, this is paper. 0, 0, 0, 1, this is scissors. And each one of these vectors basically put a 1 in the slot that gives us the right answer. And so that's what this does. This forces a number 3 into something that looks like this: 0, 0, 1, 0. That's what that does. Okay. The next thing we're going to do, so let me run this. Let me run this here. So, yes, I will install it. By the way, I redid this entire thing, and I added a little explanation on how to do this if you're doing Python. So we'll give this a second. Oh, and I need to restart this so it's using the right thing. Okay, so let's run this again. Hopefully it works, and if it doesn't, then apologies. I tried it literally an hour ago. Okay, so it loaded everything up. These are just functions. You can see that it loaded them up. And then what this does is this says go into the images folder, and I want an image folder data set. And it gives me the actual classes. So if I go over to Jupyter, you'll see in classes right here, this is this variable right here. You can see that 0 represents none, 1 is paper, 2 is rock, 3 is scissors. That's all that is. And then this part here says how many do we actually have? And then we split the data set into 2. 1 to do the training and 1 to see if we're any good at this. So 80% of the pictures that I have, we're going to use to build the model, And the 20% left, excuse me, we're going to use to see if it's any good at it. That's it. So that's how we test it. So there's the training data set. And there, let's see, did I not? Okay. And you can see that there is the training data set. It's 291 pictures. There's the validation set. Looks like there's 73 pictures. And that's what we're going to use. 2 data sets to do this entire thing. Okay. Now here is a little, this is a little like, how do I say this? Like, not shopkeeping. There's a word to keep things tidy. This lets me know whether or not to use a GPU or a CPU when I do this stuff. And it turns out that if you're wondering, well, why the heck are GPUs so useful to machine learning? Well, whenever you play a video game, you're basically multiplying a bunch of matrices together really fast. That's what GPUs do. And if you think about it, remember, we're using pictures that are like, 3D matrices, and we're going to be doing a lot of multiplication, division, and whatever. It turns out if you have a GPU, it makes it go really fast. And let's see. No, this is not what I wanted. Let's see. Task Manager. I'm going to show you here is my setup, and this is the GPU that I'm using right now, which is a nice one. It's a nice GPU. So I'll put this right here. You can see I'm not really using anything. And once I get this thing going, you'll see that it will do it. Okay. So now it's saying I'm using the GPU, which is a CUDA device. Now this is the model shape that I'm using. Okay. This is not a simple linear regression. This is a deep learning model. Well, semi-deep. Basically what I'm doing is I'm using a model that's been built before, and then I'm adding a little bit of my stuff at the end. So I'll tell you what this does. This MobileNet V Small, or almost all of these models, what they do is they take an image, and then we transform it into the 224 by 224, and then once it goes through this model, out comes 1,000 numbers. Like X1 through X 1,000. What I want to do is I want to take these numbers and map them down to the 4 that we want. Like, so if the biggest number here is in here, we're going to say none. If the biggest number is in here, we're going to say rock. If the biggest here, paper, and then scissors. So you can see that I'm basically adding a little linear thing at the top, right? And then I'm adding the classes. And that's it. This forward thing basically says if I get an X, which is the image, we're going to pass it into this layer. Out, it's going to come. We're going to run this function, and then we're going to do what's called the softmax, which basically makes them all sum to 1. And so when you see probabilities come out on which one is which, this is forcing it to look like that. Okay. There you go. So there is the actual model. Okay, now, if I've lost anyone, please ask me questions now, because this is where people start to be like, what the freak are you talking about, Seth? And there's no dumb questions, because we have time and I want you to understand this. By the way, here's the model.
Is it when you split the data between training and test?
Mhm.
So what is the proportion? What ratio did you do?
I did 80% for training and 20% for training.
Okay. So is it like a norm for the graphic application? Because
Yeah.
usually data for okay.
But go ahead. Usually, I'd love to hear your
Usually
perspective.
for number crunching, I mean, I'm taking in some training, so I learned like 70-30 is the ratio. You split the data, but 80-20
yeah.
is for graphic application.
No, I mean, it's really, and that's a really great question. I'm glad you asked it. It's basically whatever you want, because you can also split this into, I've seen like 70, 15, 15, right? They use this to train. They use another one called a test data set that's testing during the training. right? To make sure we're going on target. And then after the training is completely done, they use a validation. So I've seen that too.
Okay.
So there's multiple ways of doing this. It's really up to you. But basically the idea is, how do you know it's even working? You have to split your data up. Great question. Any other questions? The question you should have is, why did you choose this? This is it's an important question, because it's like, I got to this and I'm like, oh, it's this easy. And you're like, this easy how? You ever seen that cartoon? What's that cartoon? It's not a cartoon. It's like how to draw an owl, right? And it's like, draw 2 circles. And then at the end, there's like some beautiful owl picture. Doesn't it feel like I kind of did that a little bit? Well, it turns out that with vision in particular, there's a ton of models that have already been built that people have found to be kind of useful. Let me show you where I find them. Model Zoo. Model Zoo. We'll just do Model Zoo. Here are a ton of models and what they're good at. And you start to get a sense for what these things are good at. Like, for example, I see DC GAN. I start to get a sense for this is a generative adversarial network with some convolutions in it. I look at a PyTorch GAN, generative adversarial, RCNN is for object detection. This is for, you start to get a sense for what these are, and you start to find what they're good at, right? So let's see. So for computer vision, here's a bunch of them that we're using. You can totally see them in there. Also, what's cool is you can actually models. These are all the ones that are just built into PyTorch, for example. You can just sort of search through them. I chose MobileNet because it's small. There's other ones like a ResNet, for example, or there's a ton of them. And I just used the one that was the smallest. This construction here that you're looking at is how PyTorch does it. Basically, every model is built off of this base class called a module, and the only things you have to implement are the forward. And the forward just says, this is how, if you get the object, this is what you return. So that's what this model does. So whenever I use this model, you'll see I use this model right here. The model is passed in. I just call it with an X. It's running this forward algorithm. And this init is what you would call a constructor in C#. That's what this is. All right, any other questions? Oh, and this part right here says move all of the execution of this to the GPU. All right, questions?
How do you know when your training is good enough? Like, is there like, are you just doing that based on the set of images you have, or is there some kind of quality function or something that you use?
Yeah, it's a great question. How do you know if it's doing the right thing? Well, first, we separated our data out so that we train on this, and then we see if we do well with the validation data set. That's the first thing. The second thing is that, this model does the prediction. But when we train, we have a function called the loss function, and the loss function tells us how good or how crappy we are at it. And the larger the number of the loss function, the crappier we are at it. And what happens is when we train this thing, we create a loss function and an optimizer that minimizes the loss with respect to the model parameters. And so what happens is every time we train, and I'll go back up to this every time we do a training, we batch all the pictures together, we get the X and the Y, we here predict, and then we measure, okay, this is what we predicted, this is what the right answer is, how crappy were we at it? And what this does is it uses the optimizer to go backwards in the function to update its parameters to do a little bit better. Now, the way that it does this is it uses calculus. And I know everyone's like, oh, calculus is too hard. No, everyone's doing calculus when they're driving their car. Like, you know not to hit somebody, you know how fast to slow down, you know the optimum speed to go so that you don't, get a ticket. Basically, this function is like some crazy like 40 function, and what you're doing is you're trying to find the minimum of the loss function so that the loss that actually encapsulates the model minimizes the parameters inside the model. And in the model, there's a ton of numbers that it's saving. So this MobileNet V small is basically has a ton of numbers in it that it multiplies all the pixel values by, and then it does another function over, and then it multiplies them again. And those numbers inside that model are what we're trying to find the best numbers for, and we use calculus effectively to do that. And so there's a loop that goes over the pictures, and the longer you do it, the better it is at it, because it's this huge function. And so it's just like marching along saying, is this the best spot? No. Is this the best spot? No. Is this the best spot? No. And then it might get stuck here, but it can jump out. Is this the best spot? No. Oh, is this the best spot? Oh, this feels like the best spot. We're going to stop. And so as you're searching around, you're basically trying to find the best thing, and you have to like scale your steps. Like, for example, if you're like, I'm here, and then I want to optimize, and I go too far, you might end up here or whatever. And so that's what this is doing. And then this test basically just says, how good did we do based upon the loss function, and how many did we get correct? So what I'm going to do is I'm going to run this so you can see it happening. Okay. So now we're going to get the training, and for every epoch, which means how many times do we go through the data, let's see how it does. It looks like I have 20 epochs, and you're going to see that the loss, we want it to go down, and the accuracy, we want it to go up. Okay, so notice that the accuracy is garbage. Looks like the loss is going down, so we're going in the right direction. The accuracy is going up. Do you see that? So this measures how crappy we are at it. This is testing the accuracy on the test set. And notice that fairly quickly, after going through the data set like 20 times, we're starting to get up to about 98% accuracy with a really low loss. Remember, the loss at the beginning was like 0.82, and the loss at the end was 0.02. And then the accuracy went from 15% accuracy to 98% accuracy. Okay, any questions about this? Did I answer your question about how do I know if I'm doing well?
Yeah, that helps. Thanks.
Cool. Okay. So this is generally where machine learning stops, and everyone's like, oh, we made it work. And everyone's like, okay, well, what do we do now? So I'm going to go to the next step, which is how do we put this into a software, right? Because you're noticing that there's really no output from this. And so once you get things working in notebooks, I basically put things in Python files. So here is the vision model again. The only difference now is I added a save method to this class. And this save method just says, hey, if the model directory is not there, add it. Otherwise, save this, and this saves it in the standard PyTorch format, which is kind of cool. But this saves it in the Onyx format, which is like the PDF of deep learning, where you can use it in like ML.NET, for example, directly in your software. That's the difference there. These are the get data sets. Notice that it's saying to use the data images, and this is the same stuff we saw before. Exact same stuff we had before. The training function is exactly the same that you saw before. This is the test function, and then this is the main. I get the data sets. I get the data loaders, which have the data sets in them, and then I get the loss function. This stands for binary cross entropy loss, and then this is the vision model. I move it to the right thing. This is the optimizer, and then I train. So let's go to the terminal, and let's just call it, 25 times. Python, and this time it's going to save the model. Questions while this is going on? This one you're going to see more output. You can see it getting smarter. this is doing. Any questions, by the way, while this is going? It's going to go for about 25 turns. By the way, if I didn't have a GPU, this would take much longer, probably a half hour.
So this is another side question, but Vince and I, we were chatting, and he was talking about how there were issues with the machine learning, and then I asked, was the data cleansed properly before using it for ML? So is that something you can touch on?
Yes. So I usually like using images. I'm a computer vision guy, not like a thought leader kind of guy, but a computer vision is like pictures, because pictures are pictures and they're always it always is what it is. But if I did not label them correctly, that would be a problem. Other times when you're doing machine learning, the kind that I think Vince was talking about, it's usually on squares of data, right? Like age and gender. Well, you shouldn't use any of these features actually, because you get into the problem of ethics. So let's just say you have a C, G, T, whatever. The numbers in here matter, right? Because they could screw up your training. And so if you have empty data or your data isn't useful, like for example, if you're putting an ID into your machine learning, that's the worst kind of data to use because it's not predictive of anything. Maybe. It might be that everyone after, ID 20,000 is something, but usually that is a high entropy column. And so you have to spend some time making sure your data is right. When I collected this data, what's nice is I built a web app that I just selected rock and I just did rock and it captured all the pictures of me doing rock. And so it was easy to do that. But sometimes you got to spend some time cleaning your data. Now, the reason why I didn't comment on that too much is because that is hairy. And that part everyone kind of starts to understand once you do modeling for the first time, because it's like if your data is garbage, then your model will be garbage. If your data is racist, your model will be racist. If your data favors one person over another, then your model will too. If your data, it's just that's just the way it is. Now, that's an important thing to talk about, but maybe we'll leave that to some other time. But yeah, you got to spend some time making sure your data is correct. Like if these things were not labeled properly, like I could name this dog, cat, bear, and scissors, and it would learn that. And it would label them that way. I don't know why it's not getting any smarter. So let me put it at 30 because it should get to about 100. Let's see, 95, 93. I'm going to give it 35 epochs and then do it again. Any other questions? Oh, by the way, notice they're model folders. I'm going to delete it again. Any other questions about this stuff?
So this ML.NET, the behind the scenes, is it using Python or how does that work?
No, ML.NET was a project that came out of Microsoft Research many years ago. And so it's using older style technology that then was ported into .NET because that's what Microsoft used. And then they open sourced it and put a product around it. So it's custom machine learning code that was written in C#.
Okay.
Yep. Looks like it
So
got
let's
smarter.
say
Yeah, go ahead.
let's say I have a model developed in Python, and how do I consume that in .NET?
Ah, great question. So let me train it one more time because I think I need to get my model to like 100% because let's do that. So the question is, once I train the model, how do I actually use it in software? Because training and inferencing are two completely different jobs, right? Right now, this is not something you would ever do as part of your app. It might be, as you're trying to make your model smarter and smarter and smarter. Oh, wow. Now it's at like 100%. Yeah, look at that. Yeah, I think I maxed it out. Cool. But then there's this question of model freshness, so to speak, because as data shifts, you might have to retrain your model, etc. But notice that this model now is like, look at this. I mean, it knows its stuff now. let me show you the output of this thing. So I'm going to go over here. Notice the first thing I did is I saved this JSON file with the classes. So if you look at this JSON file, notice that it basically just has the classes. So I know that if I get an index of 0 as the answer, then I know it's none. Index of 1, 2, 3, 4. Okay. That's the first thing. The second thing is I saved it in the standard PyTorch format. This is how you save PyTorch models. Now let me show you what actually is in the model. So let me go to Reveal and File Explorer. And I'm going to open this PTH file in a program called Netron. Notice that Netron basically just stores all of the modules, the nn.modules, but it has no notion of how these things are connected, because in PyTorch, this class tells you how these things are connected. And so what it does is when you new up this thing, it will basically load up the weights into this structure. Onyx is a little bit different because Onyx is like supposed to be like the PDF that anyone could use them. The Onyx stores the weights of those modules as well as the connections. So let me show you. The Onyx model will look a lot more interesting. So here comes the input image, right? And the input image has three. Sorry. Oops. So the input image has RGB 224 by 224. This just says is there's one of them. When we were training them, we would pass in like, batch number at a time. I think for us it was like, 32 images at a time, but we're just going to pass one image at a time. And then the output is a prediction, and the prediction is this vector of size 4 that's going to tell us some numbers, and the one with the highest in the argmax of this is going to be the answer. So the image goes through this thing. And the first thing it goes through is this convolution. And what this convolution does is it does like some fancy multiplying by these numbers. And then it goes through and it does a lot of multiplication, some convolutions, and then it just does this all the way till it gets to this thing, which is a generic matrix multiply. Notice it goes from 1024 to 1000, and then this is the special sauce we added at the end to make it go down to 4, and so the output is going to be a 1 by 4 vector. Cool. So this is an actual machine learning model, a bona fide. You can see it. This is deep learning. This is one of the smaller models, and it's faster to show what's going on. And basically what it learned was that in order to do the best with all the pictures that I gave it, these are the numbers that it needs to use to multiply those pixels by. And then it passes them down. Questions? Okay. All right, so now I'm going to use this in a program. I'm going to use the Python one because you can, but because it's the easiest for me. But if you wanted to do like ml.net Onyx, you can see that there is a way to load Onyx things using an ML context, and you can see this is a Netron, and this is the Onyx input. You'd have to make a matrix to put it in there. And you get this prediction pipeline, and once you load it up, you apply the Onyx model with the inputs, output columns, input columns, and the model path, and then it looks like you have to do a fit, which I don't know why it does this. But then you do I think this is how you have to do a prediction engine, and then that does the prediction for you. But that's the one. This is why I don't like ML.net, because I wish you could just load the Onyx model, but instead you got to do this like prediction pipeline, which we're not. See, it's like literally you have to fit an empty pipeline. This doesn't make sense to me. I wish there was just a ML context.load Onyx model and that's it, but you don't have that. So this is how you have to do that in .net, but it is possible. Let me show you how I load it up in Python. So we're going to do this scoring file. And this scoring file has an init. It looks for the model path. It looks for the JSON file. It loads up the vision model with the right classes. And then notice that it loads the state dictionary from the model path. it sets the model up for evaluation, and then there's the transforms. And so whenever an image comes in, I'm going to give it a URI. It's going to load the image, convert the image from the request, converts it to RGB. Then I do the transform, call it on that picture, and then get the prediction. Let me actually, how about this? How about I just literally step through it so you can see it happening. So let's run this here in Python so you can see with breakpoints and all. Okay, so is it stopped? Oh, there we go. So there's the model directory. Notice it's just model. So I'm going to F10 here. There's the model path in its absolute glory. I'm going to try to load the JSON file. There it is. You can see that the class is here. Excuse me, rock, paper, scissors. Then I'm going to load the vision model that has the right classes. And you can see if I type the model in here, you can see it's just a big old fat thing of, model stuff. Then I'm going to load the model variables, the actual weights that it learned, set it to eval, and then build this transform. Okay, so now that we've done that, I'm going to pass it this image. Let me load this image up so you can see that's me doing scissors, looks like. So I'm going to F11 here. The first thing we do is we're going to say, hey, we're loading the image. There's the terminal. The terminal should have it. Loading the image. Then I'm going to open the image from the internet. So there's the response. And there's the image, right? You can see it's a PIL, pillow image. Then I do a transform, and this transform will produce this vector thing. Here, let me go to the debug console. So there's V. You can see it's just a huge image. So it looks like it's -1 or 2 to. So I by the way, these normalization constants are the ones that they tell us to use in PyTorch. So everyone just uses them. I don't know why, but I bet if you change the numbers to be between 0 and 1, it would still work. But this is the actual image of me doing scissors, but in number format. I'm going to pass it to the model, F10, and then the response, let me show you the response. The response is this thing right here, right? So this obviously is super small, super small, super small, not small. So this is none, this is rock, this is paper, this is scissors. So what we're going to do is we're going to get the argmax of that one, which is going to be number 3, and that's going to say our prediction is scissors. And so we're going to predict scissors. So let's put it in the terminal, predicting scissors, and then F5 this out, and you can see all the other scores in there. Okay, questions about how I just ran this? By the way, did you know you could do this with Python and Visual Studio Code? It's pretty cool. Questions about this? Because I want to make sure I answer the questions. Yeah, go ahead. Sivaram, did you have a question?
No, I'm good, Seth.
Cool. Any other? Now let's, just so you can see that I'm not like pulling your chain here, let's open a rock up. There's me doing some rock. And let's run it again. So I'll F5 it. Let me just hit it here. And we'll do it again. So there's the model path. Cool. F5, load it up again. Loading the web image, get the image, transform. There's the response. You can see the response vector there. Let's print out the response here so you can see it. Response. You can see -5, -5, -1. So notice now it's 0, 1, none, rock, paper. I think maybe it got the wrong answer. I don't know. So we are going to be predicting rock. So I did get those backwards. There you go. So notice that this is rock, and it predicted rock. Let me put a paper in there real quick. And then we'll do this one more time. F5, F5. Uh-oh. Oh, see, it doesn't have paper. So that's why I spelled paper wrong. paper. Okay. You should probably put error checking in there, but I wrote this real fast, by the way. There you go. So notice that now it's predicting paper. And that's the extent of using the model. And again, I showed you a little bit on how you might load this in ML.NET. But like I said, I need to talk to them about making it less clunky. I did, but they didn't like what I had to say. But this was years ago. I should probably ask him again. Any questions about this? Okay, so let's go back to the other questions that we had at the beginning to make sure I answered them as well. ML.NET training, why does it get better? So ML.NET uses something called automated machine learning in the back end. And so what it's doing is it's trying a lot of different machine learning models. And so the longer you let it go, the more models it can try. And as you saw for each model, the more time you give it to optimize its parameter, the smarter it gets. So that's why. The longer you give it time to optimize its internal parameters and try different models, the better it will get. Does that answer your question, Sam?
Somewhat. So when I run through, let's say a set of data, let's say 1,000 records, and I give it 5 seconds to run through it, it'll go through a certain set of algorithms.
Right.
Let me rephrase it. If I give it 30 seconds, it'll go through all the algorithms. And then if I give it 60 seconds, it'll go through all the algorithms twice. So why does it keep repeating the same algorithm and then get better results as it goes on? Why not from the first run?
So my sense, and I don't know how it's implemented. Like I said, I have some problems with ML.NET. But as you notice that when I trained my thing, let me go up. Oh, dang. Oh, it's right here. When I trained my thing, I want you to see something. I don't know if it cached it. I don't know what happened. Oh, no. There you go. So notice that it started at 28. And remember one time when I did it, like by epoch, I think it was 25. It was like at 95%. Look at our epoch 24, the second run through. Sometimes it gets lucky because basically it's just trying to bottom out the function for that model, the loss function for that model. Now, if you're giving it some time, that hopefully, I hope it's saving the models from before that it's tried and just giving it more epochs to run through. And that's why it would get better. That would be my guess. That it's saving the models that it's tried before. And if you give it more time, it's now 30 seconds is actually not a lot of time. Generally, good models that you build take, like the big models like GPT-2, for example, take about an hour and a half to refine, but then they run in like, a second or two. So 30 seconds is not, sorry, my earpiece came out, not a lot of time. So does that answer your question? I think that maybe if it was me, I would cache the models and then give it more epochs to run through.
Okay.
But I don't know what they're doing.
So going along those lines, if I train my model on 1,000 records, and then let's say I feed it another 2,000 records and train it again, does it do away with the previous training of that first 1,000, or does it just simply build on it?
It depends. Like, are you aggregating all the data together?
No, they're separate.
Okay. So if let's just say, I'll give you an example. So that's a great question. So just to be completely clear, you're saying if I trained a model on 1,000 records, then I load that model up and train it on 2,000 more. Is it going to get rid of the 1,000 from before? Not really. I mean, it depends. If the new 2,000 data set is wildly different from the 1,000, then yeah, it's going to optimize for the second. But it will have a better starting point. So this thing right here, the reason why there's this pre-trained thing, let me show you something. I'm going to change this to false. This is just going to load up randomized weights. If I say pre-trained equals true, It's going to load up MobileNet that was trained on something called ImageNet, like tens of thousands of images. And then they trained it to do specific tasks, and then they just saved the weights for me, right? If I do pre-trained equals false, this thing is going to take a lot longer to converge because it has no starting point. So it's going to start from scratch. And so hopefully it doesn't prove me wrong, but notice that the accuracy, notice how long it takes now for this thing to get better. Because it didn't start with something that it already had information on, which is images, right? So now notice it's starting to get better, but really, really slowly.
Mm-hmm.
So let me go back here to pre-train equals true, because this is a similar task that I'm doing to the one that this original model was trained on. Now, using a model with pre-trained weights to solve my adjacent task, that's called transfer learning. And so effectively what you'd be doing is, if the task is similar, but the 2,000 records that you have enhance the 1,000 from before, it means that your model will train faster and be better. See, I'm already at 100% accuracy, whereas before I was like struggling to break, 36. Because
gotcha.
this had numbers that it learned from before. And so that's where MLOps starts to become important. Anytime you have a model, you basically, when you retrain it, you don't want to start from scratch. You take the model that was kind of good and then you refine it. And so notice this model is already super good, right? Like 10 to the 8, 10 to the minus 2 kind of loss in 100% accuracy. Did that answer your question?
Absolutely. Thank you.
Cool. Any other questions? Okay, so let's go back to the board here because I want to make sure to answer your questions. So we did that. How do we know if we're making progress? Okay, so this is interesting, and I wasn't going to talk about this, but it was something that y'all brought up. Azure has something called Azure Machine Learning that lets you keep track of your machine learning experiments to know how good you are at stuff. Because generally this stuff is all happening on my machine. It's not easy to know what's going on. Now I wonder why this is taking so long. Here we go. So Azure Machine Learning basically is a way to run machine learning models in the cloud inside of containers, with the added benefit of being able to remember anytime you did a job. And you can see, for example, here's a job. Let me find one that's similar to the one we just did. So this is Rochambeau, which is also rock, paper, scissors. In this case, you can see all of the experiments I ran. You can see the parameter size, and then you can also go into like the actual experiment. I think I got rid of that column, which is kind of dumb. Let's see here. Name. Let's move that up. Okay. So this is the run ID for this one. It took 7 minutes to do. Cancel. So we need to save. Save this view. So now I can click on this. This is how many times I ran this thing. So I can click on this one, for example, and then I can and I ran this like months and months ago. I don't even actually remember when I ran it. But the idea is I should be able to see, like, look, I ran this December 2021, right? It took this much time. Let's take a look at some of the metrics here. You can see that this particular experiment, gosh, why is it so slow? By the way, if I show you stuff, it's because I'm like a secret internal branch of this stuff, and so sometimes they might be working on stuff. But you can see that this is the best score, which is a lot better. This is also rock, paper, scissors, but this is crazy good on the loss function. You can see the accuracy numbers. You can see the loss numbers going down, validation. And so, like, this is how you know if a thing is working. You can actually see the charts of this stuff going on. You can also even see, like, the output. So there's the model that was output. Let's see if I can find some of the other system logs. Wow, this changed recently. Look, it has a summary of the model for me. There's the image build log, right? You can see that it's all kind of just in here. Wow, this is a lot of stuff. This must have changed recently, which is really cool, actually. Wow, this is cool. And then here's the standard log, right? You can see this thing running. And so I have this for every single experiment that I ran. Not only that, I can look at charts for all of them. So looks like there's one of them that just actually really sucked. This one down there, and you can see that like I know exactly how long these things took, what model it ran. Looks like this is the smallest model. If I go over here and go to the metrics, you can see that hopefully there's charts in here that tell me how good this was. Wow, this one got smart really fast, but it's not the best score. The other one was a better score. Do you see? And so to answer your question, how do you know if these things are actually doing or we're making progress? This is how. You need to have some kind of tool that helps you keep track of all of these things. And the cool thing about this is, like I said, is this will all run in the cloud inside of custom containers. So I build environments where these things run. So for example, that one that I showed you uses PyTorch Lightning, and it's these are like environments that we build, and so it always works the same way every time. You can see progress that way at an organizational level. Who asked that question? I want to make sure. Did I answer the question on how you know if you're making progress? This right here. We good? You have to have a tool to do that, and the tool we build is Azure Machine Learning to do that. You can see it's all here. All right. Any other questions? Oh, good place to get started. You know what? Really, it's just a question of the first thing I would do is I would download a model and do inference on it or try a model out. So how does one do that? The best place to go is Hugging Face, huggingface.co, I think. My internet's so slow. I don't know why. Huggingface.co, and there's models there that you can download and try and use. You can also convert them to Onyx format and maybe load it in your .NET program. And so let's just say you want to have a really interesting sentiment analysis built into your .NET program. You could go to huggingface.com. I spelled it wrong. Hugging Face here. Huggingface.co. You can go and find the actual model and just download them, right? So I don't know. Let's just say you want to do image classification. There's a ton of them here. You can download them, or summarization models. You can download them. Let's see if there's any from most downloads. So there's DistillBart CNN. Here's this thing. Here's how you get this is how you do the stuff. Here's the community questions, whatever. You can download it and try it. There was one that I tried, like an image denoiser, and that one actually, it worked really well. I just downloaded and tried it out. So I would go there and try it out, and just reading, like just build your own first model. It's just trying stuff out. Okay, any other questions before I turn the time back? Cool. So hopefully, just to summarize, what you saw is we discussed like what machine learning is, right? I showed you the landscape of AI versus ML versus DL, AI, artificial intelligence, machine learning, and deep learning. Then what we did is I showed you in a notebook how someone would go about, loading these things up and training them. And then I showed you how you would train them in a more productive way, because this now you can save and put into anything, and you can run this in the cloud. I showed you how to save things to the Onyx model format. I showed you what the artifacts were of machine learning. It's actual files, right? These are the files that you would use. And then I showed you how you would actually use those artifacts in a program. I also spent some time, because this is the .NET user group, I spent some time showing you, hey, this is how you would do it with ML.NET, for example. as well. And then finally, I showed you how you would use a system to keep track of your jobs, the type of compute you would use, and the models that you would build, and the data that you use. All right. Any questions beyond that before I turn the time back to Sam? All right, Sam, back to you, my friend.
Actually, before I take the screen back, one last question.
Sure.
Any recommendations on tools for data scrubbing?
That's the ugly part of machine learning. I don't have any recommendations because it depends a lot on your data, the type, the kind, and then the three V's, volume, velocity. What's the other one? Volume, velocity, variety. It all depends on. And I suck at the data part. I'm really good at the model part.
I have a suggestion for that.
Sure.
Open Refine.
Oh, let's look that up. Love it. This is delightful. Look at me. I'm learning stuff. Okay. I love it. I'll take a look at this. This is nice.
Yeah, same here. But essentially, I think you need a subject matter expert whenever you're going through the data to look at the three V's like you mentioned.
Yeah, and like I said, there was an expert because I used to be in DevRel, and she was our expert, and she's like, Seth, you're like the guy that takes water out of the faucet and makes fancy drinks. I'm the person that has to get the water from the well into the city pipes and into your faucet. And I was like, I understand your job now. I don't want to do it.
Good analogy.
Yeah, she's awesome.
All right. Any other questions for Seth? I guess not. All right. Thank you very much, Seth. Highly appreciate it.
Thank you.
Before everyone takes off, just have a couple closing announcements. And let me go ahead and take back the screen if I may.
Perfect.
All right. Also, in addition, let me post a message in chat, and that'll include all the links that are needed. And we'll go through those in just a second. Whoops, wrong one. Just when you think I would have figured out cut and paste by this stage, it still comes back to haunt me. All right. Son of a gun. There we go. It'll happen. And success at last. All right, so I pasted in the chat window a couple links that we're going to discuss. So with regards to the presentation, it will be, it is obviously being recorded and will be posted to YouTube shortly in a couple days after the editing. If you would please subscribe to the channel to get upload notifications. Likewise, with the tech events that we'll go through in just a second, those are going to be posted on my blog, samnasser.blogspot.com. And then lastly, the feedback eval, the link is also posted in the chat. If you would please take a moment to fill that out so we can provide Seth with some feedback. Again, special offer from Manning.com, 35% off at the selection of books. And that link is also posted in the chat along with the discount code. As far as upcoming events, on July 7th is the Twin Cities.NET User Group happening in Minnesota, and they are meeting online. They're going to be discussing logging and .NET Core. On July 13th is Azure Cleveland, and the topic for that will be posted on the meetup site as well. Same thing with the Great Lakes User Group .NET. They meet on July 21st, and you can find all their meeting information as well as all the other user groups on meetup.com. And then for July 28th will be the July meeting of this group. We don't have a speaker lined up yet, but it's definitely in the works. And once we have everything confirmed, I'll be posting it on the site. With regards to conferences, July 29th is JavaScript and Friends happening in Columbus, Ohio. Also on the same day in Cincinnati is Cincy Delivered, and the information for that is available at cincydeliver.org. August 8th through the 10th is Kansas City Developers Conference, or KCDC, and the link for that is kcdc.info. And then August 17th through 19th is Codepalooza happening over in Louisville, Kentucky. As we always like to do, discuss job openings. Tech Systems always has jobs listed at techsystems.com/IT-jobs. But in addition, always like to ask who's hiring. Anyone hiring at your place of employment? Going once, twice. All right. Anyone looking for work? If you come across a job opening, or if you are looking to change jobs, feel free to email me. I get emails from recruiters at various times, so I'd be happy to connect you. And with regards to my contact information, if needed, you can email me, snasser@nistechnologies.com. You can also find me on Twitter @SamNasser. And then the link to my blog as mentioned earlier. And lastly, I invite you to connect with me on LinkedIn. Seth also posted some careers at Microsoft, and the link for that is careers.microsoft.com. Thank you for that, Seth. And once again, thanks to everyone, and thanks to Seth for a great presentation. Thank you all for attending, and look forward to seeing you all next month. Good night, everyone.